So,
yeah, well, thank you. Most of that reported as
so do I have to, yeah, this much I can manage. So it's a pleasure to have now a lecture by Professor Hughes, who I might add is one of the founding members of the festival, from having attended every one of them from the very first. And let's see his, what's his story? He's from Oxbridge, with the ox before the bridge, which I suppose is the proper order. And then there was some expedition to Colorado, but then back to Cambridge, right? And then on to sunny Leeds, where he's been ever since. And he's known, well, for magnetic buoyancy, which we'll get a dose of again here. It seems one can't escape it, and also dynamo theory, and takes an interest in layering, and does many things when he's not watching football. And to give you a sense of David's priorities in life, there was about a month or two ago, there was an article in the New York Times about the social classes at Oxford, and in particular, the sort of stratification. And in particular, it described the importance of the debating society and the machinations of their soon-to-be former prime minister in controlling the debating society. And in it, that group classified the student body in three sort of categories. At the highest were the toffs, then the tugs, and the bottom were stains. Okay, and the tops were from the really fancy schools. The tugs were the sort of the lower but still acceptable, and the stains were the rabble. So I asked David, which one of these were you? And his response was, oh, we didn't have any of that crap that I can remember. We had none of that on the Jesus College football team, which gives you a sense of his priorities. So with that, David.
Thank you, Pat. That was quite an introduction. Right, so as Pat said, this is going to be about magnetic buoyancy and the anelastic approximation. So all these things I will explain as I go along. So this is some work that I've been doing for a year or more with Frederick Zoltinsky, who that's already failed, who some of you will remember. Frederick was came to the festival probably in 2017, I think, and did some work with Xavier when he was here. And he was a postdoc in maths when we did this. He was my student before that. Now he's in earth sciences, still in Leeds. And Evie Casale. Evie has also been to the festival, one of the early ones, probably 2003. If after this talk you feel the need for more, it's all in this quite long JFM paper. It's full of epsilons. So if you like epsilons, it might be to your taste. If you don't like epsilons, it might not be. So the title, this was the original title of the paper, and it was a sort of homage to a paper by Ed Spiegel and Nigel Weiss in the 80s, who had a paper called Magnetic Buoyancy and the Buoyancy Approximation. So we thought it would be nice to have one called Magnetic Buoyancy and the Anelastic Approximation. One of the referees objected on the grounds that it was not sufficiently descriptive. So we ummed and ahed whether we should be descriptive or concise. In the end, we went for descriptive. So the paper is actually, nothing's working. That's weird, isn't it? Let me try that one. Ah, now really nothing's working.
Exit and go back to
Yeah. How do I exit from this? There's an escape exit. Okay.
wonder if this one's going to work. Oh, yeah.
Thanks, Guillaume. So this is actually the title of the paper, which is not nearly so snappy, but it gives a better impression of what's going on. So all of these things I will explain.
Okay, the light doesn't work.
So this at the heart of it is this instability. Okay. It's an instability which is described by compressible MHD, that's for sure. However, you might want to describe it in a simpler system to compressible MHD. And that's really what this talk's all about. And I'll explain why it was even an issue. Okay. So this is what I'm going to talk about. So I'm not really assuming that you know any of that you come across any of these things. So obviously many of you have. So I'm going to spend some time just talking about this instability, what it is, why we're interested in it, its various manifestations. So magnetic buoyancy is quite an interesting instability. It's got all kinds of different facets to it. Then I'm going to introduce the Buoyancy and the anelastic approximations at the beginning with no field. And this is really, this was the question that was sort of behind this work. How do you get magnetic buoyancy into these approximations? Well, the first question, how can magnetic buoyancy be treated self-consistently in the Buoyancy approximation, that's what Spiegel and Weiss addressed back in 1982. And we'll come to that. And if you've read that paper, then you'll know that to get magnetic buoyancy, this instability, which I'll describe in a minute, into the Buoyancy approximation is a non-trivial task. You have to jump through all kinds of hoops to get it in properly. And so a question that had been puzzling me for a while was, how come, well, do you need to jump through similar hoops for the anelastic approximation? Because nobody does. People take the anelastic approximation, which again I'll explain, and they say it's got magnetic buoyancy in, it's fine, or the assumption is that it's fine. And this puzzled me in a way, because for the Buoyancy approximation, you really have to do some non-obvious things. So that was the question that started it all. Whilst we were doing it, it became clear that there were lots of systems that there were asymptotic reductions of the full compressible MHD systems. And we think there were 5 sensible asymptotic reductions of the compressible MHD systems. So that's almost fitting into one of the topics of the festival, model reduction. That's as close as I'm going to get, I'm afraid. So, so we're going to look at these and how they're all related to each other. Okay. Then there's a final question that if you've got magnetic buoyancy, let's say, in the anelastic approximation, let's say, does it agree with the anelastic limit of the compressible equations? You might think, how could it not? Well, it might not. It's possible that it could not. So that's a question that we will also address. Okay. So for the next few minutes, at least, I'm just going to talk about this instability. Okay. In case you haven't come across it before. So the easiest way of thinking of it is just from a fluid parcel argument. So this is, okay, this is not a flux tube in a non-magnetic atmosphere, right? The initial state is an equilibrium state. P, rho, B, etc. are all the same at a certain height, okay? They're just functions of Z. Then you say, is that state unstable? So the easiest way of doing it is to take a blob. Let's suppose we don't bend the field lines. We take the blob and we move it up here. Okay, and we make certain assumptions. So we move it slowly and we'll see why in a minute. Okay, the field is just into the page just to make life easy. And then various things so this is just like one does to get the Schwarzschild criterion for convective atmospheres. Okay, it's just got a field in it as well. So the blob conserves its mass, it conserves its flux, hence it conserves B over rho. So if I denote changes in the blob by delta and changes external to the blob in the atmosphere by D, then I get delta B over B is delta over rho. The blob, let's suppose it moves adiabatically, so that delta B over B is gamma delta over rho. We move the blob slowly. If we move it slowly, then any pressure imbalance is modulated on a fast time scale, of course, by fast magnetoacoustic waves. So we can assume pressure balance between blob and its surroundings. Total pressure balance. Gas pressure plus magnetic pressure. And you can obviously manipulate those in a very straightforward way. And you get this nice criterion, which is that instability, the blob will carry on rising if it's less dense than its surroundings. In other words, if delta rho is less than D rho. Obviously, you don't want deltas in the answer because they're just something to do with internal dynamics of the blob. You want D's in the answer. They're to do with the external atmosphere. And you can write this in various ways. This, I think, is the most instructive. It says that if B over rho falls off sufficiently rapidly with height, then you can have instability. Okay. Of course, if there's no field, VA is the alpha speed, CS is the sound speed. If there is no magnetic field, this is just the Schwarzschild criterion. Okay. From the point of view of this talk, this is a very important point, that the magnetic pressure here of the blob influences the density of the blob. Okay, that's absolutely crucial for everything. If magnetic buoyancy is going to be important, the magnetic pressure must play a role. Okay, so that's going to be a sort of guiding principle
For a lot of what comes next. Okay, please ask if any of this is unclear.
So it's got an interesting history, magnetic buoyancy. So the first paper, I think, is by Newcomb in 1961. So Newcomb used the energy principle of Bernstein et al. To show that that criterion that we've just derived, which in some sense is just local, is actually much more powerful than that. Newcomb showed that if that criterion is satisfied anywhere in the fluid, then you will have instability. Okay. Because, you know, through the energy principle, you can get both necessary and sufficient conditions for instability. He also showed, though he didn't actually write it like this, he wrote it in a way which hid the magnetic field. He got rid of it, so his criterion didn't actually include the magnetic field. So to get magnetic fielding, you have to use the magnetohydrostatic equation. So he wrote, his actual formulation of it wasn't so apparent. Anyway. In the same paper, he also showed that the instability to 3D modes, so what we've just considered are 2D modes where the field just doesn't bend, so-called interchange modes, whereas 3D modes, it's similar, but this is a more readily satisfied criterion. Okay, it's easier to have B decreasing with height than B over rho decreasing with height. And so 3D modes are more unstable, which on the face of it, you might think it's unusual because you've got to do work against tension, of course, to destabilize a 3D mode. And there's a lot of different explanations in the literature about why 3D modes are more unstable than 2D modes. We had our own take on this way back with Fausto Catania. What we believe is that, so to get density variations, you've obviously got to do work against gas pressure to squish the gas. If you've got interchange modes, you can't avoid doing work against the magnetic pressure because they come together. They're inextricably linked. Whereas in 3D, you can move more or less along the field. Obviously, you need a bit of up and down, otherwise you're not going to get an instability, but you can have a predominantly horizontal motion. against gas pressure, which gives you density variations. And that's why 3D modes are more readily destabilized than.
Just to be clear, the 3D case is what the astro world is referred to as the Parker instability.
Yeah, absolutely. That's right, Pat. Yeah. So,
But they sell it, of course, as a kind of nonlinear process.
Parker, well, yes, they sell it all to do with unburdening the crest,
Right.
stuff running down the hill, pushing down the valleys. I don't think that's really true. If you look at actually what the flow looks like, that's not what happens.
that is indeed how Parker sold it. So yeah, that's right. So in the astro world, especially the 3D one is called the Parker instability. Interestingly, actually, Parker's paper in 1966 is a 2D the other way. 2D in the plane of the field, if you like. So the field lines get bent, but it's actually 2D. Now typically that is a very hard case to destabilize. Parker took a special case where it worked, actually. So yeah, so in the astro world, it's always called the Parker instability. Newcomb, to my mind, doesn't get the credit he deserves. It's not often referred to, but this paper is not often referred to in the astro literature, but it is the first paper, in my view, that does magnetic buoyancy instability, and it's very nice. Parker in 55, Parker had two amazing papers in 55. He had a dynamo paper, mean field dynamo paper, and he did have a paper on the buoyancy of isolated tubes. So he did introduce the concept of magnetic buoyancy earlier, but from the point of view of a rising tube, which is not an instability, it's a lack of equilibrium. So in 66, he did the instability. Okay, so actually what I'm going to talk about today, diffusive effects are not really very important, but they are important in other contexts. So this is just to try and sell magnetic buoyancy to you as to why, Pat says I've been interested in it for the longest time, which is probably true. So I'm just trying to explain why there are things in here that are of interest. So in the magnetic buoyancy problem, there is, of course, diffusion of magnetic field, there's diffusion of temperature, there's also viscosity. So you can think of it as a double diffusive problem. Now, under certain conditions, which we might come back to later, and the certain conditions are quite restrictive, it's this Buoyancy approximation, which I haven't dealt with yet, and 2D non-bending of the field lines. There is an exact analogy with the problem of thermohaline convection. So thermohaline convection is where you have typically salt and heat. Double diffusive convection is where you have two contributions to the density that diffuse at different rates. And in the oceans, it's heat and salt, okay? And heat diffuses much faster than salt. So the analogy is that salt is like minus magnetic pressure. That's the easy one, but temperature in the thermohaline problem does not go over to temperature in the magnetic buoyancy problem. It goes over to some combination, linear combination of temperature and magnetic pressure. So the nicest way, without going into all the details, the nicest way of seeing the difference, I think, is to introduce Rayleigh numbers. So these are the standard Rayleigh numbers that many of you will have come across. There's a heat temperature Rayleigh number and a salt Rayleigh number. The thermal Rayleigh number is always defined. The convention is that positive thermal Rayleigh number is destabilizing. Solutal Rayleigh number is not defined consistently, as I've got it defined here. Positive solutal Rayleigh number is stabilizing. Okay, that's the more common thing. Now you could have Rayleigh numbers for magnetic buoyancy, right? You could have instead of the temperature gradient, you'd have the subadiabatic gradient. And instead of salt gradient, you'd have a B over rho gradient. Okay. And then these two problems do map into each other. Okay, but the Rayleigh numbers map into linear combinations of each other rather than, it's not that salt Rayleigh number just, well, actually salt Rayleigh number does go to magnetic Rayleigh number, but the other one's not true. So this is actually what happens. So this is a diagram that many of you will have seen before. This is double diffuse, this is thermohaline convection. So destabilizing temperature gradient and stabilizing salt gradient. So this bit down here is what is a direct instability, what's often known as salt fingers, and up here there is an oscillatory instability. And for the magnetic buoyancy problem, it's similar in that there is a magnetic fingering instability, but there is a clear, so in this problem, in the salt heat problem, the fourth quadrant is stable, really stable. Both gradients are stable, so it has to be stable. For the magnetic buoyancy problem, both gradients are, quote, stable, and yet there is instability in this fourth quadrant. Okay, so it's a sneaky instability in some sense. I could explain that this afternoon if people are interested, but it's not germane to this particular talk. Okay, this is my, oh no, this is one of my only two view graphs. So this is a talk with no movies, only two color pictures, and they're all both in the introduction. So it is, well, it is a very theoretical talk, but as Guillaume said to me yesterday, that is actually the name of the game, the name of the festival. So I shouldn't be too apologetic, he said. Anyway, here's one of the two color pictures. So what does it look like in the nonlinear regime? So this is an extreme version of magnetic buoyancy instability. This is a slab of field. So this really is a Rayleigh-Taylor instability. So it's sort of interesting. It looks like Rayleigh-Taylor, of course, and then it turns into a problem of vortex interactions. And 3D, this is a bit like what Alain was talking about on Monday. We had a discussion of the Crow instability. So what you have here, you have a layer, it becomes unstable because it's buoyant, it rolls up into vortices, and the nearest pair are the counter-rotating vortices. And so it's a sort of magnetic Crow instability. It's more, you can't, we tried this a long time ago to try and understand the magnetic Crow instability in a sort of simple model, like Crow has for his, and it's actually more complicated, of course, because Crow's discussion of the Crow instability relies, of course, on vortex lines moving with the fluid. And once you've got a magnetic field, that's not true anymore. Magnetic field lines move with the fluid. So it's a more sneaky problem, but this essentially turns into, yeah, a sort of magnetic Crow instability. And this sort of instability is believed to be important. It's the thing that's put forward most often for explaining how magnetic field escapes from inside the sun. So at the sun, of course, we've got sunspots and things which are suggestive of tubes of field rising up through the field, arched tubes of field rising up through the outer layers of the sun. And it's thought that magnetic buoyancy is the instability is the prime candidate for releasing field. Pat.
Get around, well, I mean, it must depend on the field strength, but I would think you could find cases with strong enough field you could beat Crow instability. Because I mean, the Crow instability really works by mutual induction on the vortex lines, bending the vortex lines together, and pinching and so forth. If you have to bend the field, you're going to pay a penalty for that.
Yeah, I mean, I don't know. Why do you want to beat the Crow instability?
Well, I'm just wondering if there must be a limit on how important it is in the evolution of this system. You could imagine a stronger field where it's not going to do much.
Well, that's not obvious, is it? Because if you have a stronger field, then it's more buoyant. And so you get a more vigorous instability, and then you get more vorticity. I mean, the core instability, it's not quite clear if you need to beat it in that the core instability will keep some bits down, but then arches do come up, which is what you want.
Right.
The core instability, we know that it rapidly decays into turbulence in the height of that. So how do the flux tubes actually ride out a coherent way when they're going through vigorous instability?
Oh, well, that of course is one of the great questions of solar MHD. How, I mean, even without core instabilities, how the hell do they get from the base of the convection zone through the convection zone in some sort of coherent fashion to appear as sunspots? You know, and that is not really understood. That I think, yeah, maintaining coherence of the tube to a turbulent atmosphere, turbulent convection zone, I think is still one of the great problems. Yeah. I mean, you can say, well, you know, it obviously needs twisted fields and things so it doesn't break up, but it's not really understood. It's not understood.
Yeah, because in the hydrodynamic case, we think it'd be it's preposterous.
Yeah. Yeah, and that's right. And if we didn't observe sunspots, and if you were to argue theoretically, well, these things will come down here and they'll somehow make it through all this turbulent convection and appear at the surface, people would say, come on, that's unlikely to happen. But it does happen. But it's not.
What's this key phenomenon that you feel this stuff is that you show on the right?
Well, okay, so in linear theory, so if you have no diffusion, the most readily destabilized mode is infinitely long, but not an interchange. It's like k goes to 0. The mode of maximum growth rate is some sort of, if you're slightly above the stability boundary, then the growth rate has a k in it, so it's long but not infinite. Yeah. So yeah. Yeah.
And also here we're not going to have the limited instability, so you have the magnetic field tension to go with this.
Yeah, that might be true. I mean, I think it's an interesting problem, actually. I mean, a long time ago, Mike Proctor and I tried to do the problem a la Crow, but we didn't succeed. Yeah, I mean, I don't. It might hinder the instability that Alan was talking about. Yeah. Okay, thank you. Final bit of plugging magnetic buoyancy. Okay, since it's a double diffusive system, many of you know that double diffusive systems can turn into layers. Where there's a sort of, David mentioned layers yesterday in a different context, in a step with a stepped profile. So this is some work with Nick Brummel, exploiting the analogy between magnetic buoyancy and thermohaline convection to show that you do get nice magnetic layers. So I did actually talk about this in the virtual festival last year, so I thought it would be cheating to talk about it again. This, though, just let me point something out that is of interest. This is in the fourth quadrant in the magnetic problem, the quote, stable quadrant. It's in the first quadrant in the thermohaline problem. So the temperature gradient is destabilizing, it's hot underneath, and the salt gradient is stabilizing. Okay, but both the adiabatic gradient and the B over rho gradient are, quote, stabilizing. So you think, how the heck does it manage to do anything, let alone go into layers? So how it manages it is to form backward facing steps to get around it. Okay, so that's quite interesting. Where, if anywhere, this is of relevance is in this kind of thing, so would be in stellar radiative zones. So once you've got a layered state, then transport of all sorts of stuff is greatly different to transport in the non-layered state. So one of the problems, one of the real difficult problems in stellar evolution, for example, is to understand all the transport in radiative zones. Like in the convection zone, it's fine in the sense that it's convecting and that's what wins. In the radiative zones of stars, there is a complete zoo of competing mechanisms. Okay, so this is something that should be added to the zoo. Okay. All right, so magnetic buoyancy, yeah, so in this context, it looks like double diffusion. Of course, it's more interesting than thermohaline convection. If you don't have diffusion, is not an interesting instability, right? Because it's only, if you take away the diffusion, it's only unstable if it's top heavy. And so that's not, whereas magnetic buoyancy, even without diffusion, is an interesting instability because it can destabilize states that are convectively stable. Okay, so there's all sorts of work on magnetic buoyancy, nothing to do with diffusion, and then all sorts of stuff that looks at where diffusion is crucial.
Okay, so that was my brief introduction.
Not so brief. Okay, so let's move on. So the two reductions of the full, what I call the full equations of the full equations of compressible MHD. Okay, and we can forget diffusion for this talk if we like from now on. Okay, and there are two commonly used reductions of the full equations. One, there are others, but these are the two commonly used ones. What we call the anelastic approximation and the Buoyancy approximation. The aim of both of them is to remove fast sound waves from the system. Okay, so there's an assumption that sound waves are faster, the speed of sound is faster than any dynamical speed of interest in your problem. Okay, if that is not the case, then you cannot use either of these. There are various ways of getting the Buoyancy and the anelastic approximation. So the Buoyancy approximation was first derived by Spiegel and Baronis in 1960, I think. And then later on sort of order of magnitude estimates and later derived asymptotically. Okay, so this, I'm going to pursue an asymptotic. Yeah, please. What is it? In the sun? The alpha end speed is typically small compared to the sound speed. No, not outrageously. I mean, okay, depends where you are, and it depends how strong you're prepared to have the magnetic field strength. No, I would have thought of the order of 100th or something in the tachocline. I'm not. Yeah, but don't quote me on that. I'll have to work it out. Right. So in the asymptotic, so at the moment I'm not talking about. I'll come to field. No fields for the minute. So there's two small parameters in this problem. One is one that is easy to get a grip on, d over h. So you've got a layer of depth d and scale heights of height h. Okay. So one is the ratio d over h. And the other is some measure of the size of motion-induced fluctuations compared to their basic state values. Okay, that's a harder thing. You can't kind of get a grip on that in advance. D over h you can get a grip on in advance. Here's my layer, here's my scale depth. I know how big d over h is in advance. Okay, epsilon 2 is something that you might have to kind of check on in a way. Or you might have to impose conditions to make sure that epsilon 2 is small.
Now,
normally people come across the Buoyancy approximation first because it's easier. In an asymptotic sense, it's
better to do the, well, I say it is, we'll see. I think in the next position, it's better to do the anelastic approximation first, because that's the hierarchy: compressible, anelastic, Buoyancy. Okay, so what is the anelastic approximation?
Just to be annoying, maybe I missed something. When you say you want to get rid of sound waves, don't you mean magnetosonic waves in this game?
Well, I do, except at the minute, I don't have a magnetic field. Yeah. Yeah. That's right. You need to get rid of the fast waves, basically. Hang on, Pat. So we have these two parameters, epsilon1, epsilon2. So under the anelastic approximation, epsilon2 is assumed small. Epsilon1 can be order 1. You can have stratification. You can have scale heights in your, a number of scale heights in your layer. Okay, and there's loads of studies of this going all the way back to Bachelor in 53. And there is the anelastic approximation. There is all sorts of variations on it, all sorts of flavors on it. People do all sorts of weird stuff with it in a way that they don't in the Buoyancy, strangely. So this statement, probably not in this audience, but this statement could, well, I don't know if people would object to this particular statement, but it is, I'm sure it's absolutely true. To be asymptotically consistent, to keep epsilon2 small, you must be close to an adiabatic atmosphere. People try to use the anelastic approximation away from that, where it shouldn't be used, doing all sorts of weird stuff like, if it looks like it's getting out of hand, they kind of renormalize the basic state. I don't think any of that really is valid. Okay. Probably no one in this audience is going to object wildly, but that statement. But it is used, it's used in all sorts of funny ways. It's used in ways in which people actually have epsilon2 somehow in the problem. But in an asymptotic problem, you should not have the small parameter in the problem, right? So, end of moralizing. So we introduce this small quantity, which is a departure from adiabaticity. This is a dimensionless measure of how far the atmosphere is away from the adiabatic atmosphere. And that's our small parameter. And the asymptotically consistent ordering is where the Mach number is small, like epsilon to the half. The time scale is long, and the velocity, well, okay, the velocity obviously comes from the Mach number here. Okay. And with that ordering, so the leading order, you just get the basic state. And at the next order, you get the anelastic approximation, the equations of the anelastic approximation, and these are they. And the main thing, the main message is that you don't have a d rho by dt term, and you only have a rho bar. So the bars are the basic state quantities, the reference state quantities. Okay. So the rho bar sits here, and the rho bar sits here, and rho star sits here. And through the assumption that we're close to adiabatic, these two terms are of comparable size. So this is the advection of the entropy perturbation and the, if you like, the advection of the basic state entropy gradient. There's the gas law, and there's the definition of entropy. Okay. So those, and if you wanted the diffusive terms in an asymptotic approximation, they must come in where they come in. Right, they must come in to be just of the right size to come in. So there's no, all the subtleties that I'm going to be talking about do not depend on the diffusive terms. So I'm not going to bother with them. There's a very nice rearrangement of these equations. So these at the moment involve the density and the entropy. You can get rid of the density in terms of the entropy, so that your momentum equation just involves the entropy perturbation, which is a very nice reduction, first done by Lance and independently by Buoyancy and Roberts. This is sometimes referred to as the Lance trick. There's no trick. This is as asymptotically consistent as this is. It's not a simplification. Well, it is a simplification. It's not an approximation. It's got no more assumptions. It is of the same asymptotic order as this equation.
So just to clarify, they're mathematically different, but asymptotically.
Absolutely. Right, so going down the hierarchy, so we started with the full compressible equations. We make the assumption that epsilon2 is small. We have this order and we get to anelastic. Now we take another limit of the anelastic equations, which is epsilon1 being small. Okay, epsilon1, remember, is b over h. So now you rescale, sorry for the notation, but you rescale your anelastic variables, right? They've already been scaled to be anelastic, and now you scale them again. So this is now super small, because you never really see that in the boost. Once you see the equations, all the epsilons, as I said, must go. But in terms of the compressible equations, this is how small the velocity is, and this is how long the time scale is. The upshot of the Buoyancy approximation is that we get rid of any rho in the mass conservation equation. Okay, that's really the biggest change. Well, no, two changes. And there is no gas pressure variation in the perfect gas equation. Density variations come from temperature variations. The pressure variation is an asymptotic order smaller. Okay. So those are the Buoyancy equations. Now you might say, okay, let me put magnetic fields into the Buoyancy equation. What do I do? Well, you come bouncing along and you put the Lorentz force in and you put the induction equation in, right? Why not? So these are the standard equations of Buoyancy magnetic convection, much studied, goes back to Thomson. Chandra in his book, of course, covers these. So I should put a more recent book, Proctor and Weiss and Proctor, study this system in depth as well. Hundreds of papers on Buoyancy magnetic convection. Well, meaning?
Where's the magnetic part?
Well, exactly. Well, okay. So the influence of the magnetic field is purely in this tension term. Okay. There's a bit of magnetic pressure which goes here, but the pressure in an incompressible fluid is neither here nor there. It just keeps it incompressible. So as Pat said, there is no, whether it's the wrong pressure balance, I would disagree with. It is a pressure balance in which magnetic pressure doesn't come in. And so magnetic buoyancy simply cannot be there. So there is an implicit assumption, isn't there, somewhere about the field strength. This is never really mentioned, but there has to be an implicit assumption about the field strength or other things to get to these equations rather than to get to equations in which magnetic buoyancy is included. Yeah. Which of course we'll come to. Oops. Oh, okay. Well, so I've just said that. So how should you include magnetic buoyancy in the Buoyancy approximation? And this is a question I've already raised earlier. If you just come along to the Buoyancy equations and plonk in the field in the quote obvious manner, you do not include magnetic buoyancy at all. So the question you might ask is, if you start with the anelastic equations and you merely plonk the field in the same way, well, do you include magnetic buoyancy? The answer to that is yes. Is it included correctly? That is not obvious, it seems to me. Which is why we're doing all of this. So what do we need to know about magnetic buoyancy? So the only way, it turns out the only way you're going to get magnetic buoyancy into this game is to also think about length scales of the motion. Okay. So there's actually 4 length scales. This is where it gets more hairy, but this sort of argument is familiar, of course, in tokamaks, where you really are always bothered about variations along and perpendicular to the field and things. So the 4 lengths in this problem are the depth of the layer, pressure scale height. Okay, I'm assuming pressure and density and temperature scale heights are comparable. Is that okay, Oscar? Hope so.
Yeah, that's better.
Sorry
Yes.
about that. I must have pressed a button by mistake. So you can balance, let's say, the inertial term, pressure variation with the buoyancy term, etc., etc. In the induction equation, also do a lot of algebra. But there's an interesting result to emerge, which is this, which is that the variation of magnetic pressure is related to the variation of density by this factor. D over HP times D over HP times LB over D squared. I know all the D's go, but it's still it's useful to keep these ratios in, I think, just here. So as I said right at the beginning, magnetic buoyancy will come in if magnetic pressure influences the density. In other words, this factor, these 3 brackets here, they must be order 1 to get magnetic buoyancy into your problem. And that leads to this nice relation between the length along the field of perturbations, the pressure scale height, and the magnetic field scale height. Okay. Right, so armed with that, it turns out, interestingly, I think, well, interesting to us, that there are 5 regimes, 5 asymptotically consistent regimes, 4 of which involve magnetic buoyancy, and 1, the magnetic convection one, which we've looked at, which does not. So in all of these asymptotic regimes, epsilon 2 is small. Okay. So we can introduce the alphanic Mach number, if you like, and the ratio of D over HP, which may or may not be small. So this is the standard anelastic approximation, in which there's no assumptions about length. Layer depth, scale heights of everything, variations along the field, they are all the same by assumption. And so, and also, MA squared is small, okay? Because in the anelastic approximation, you can't get the field into the basic state, otherwise you won't be close to adiabatic. Okay. And so, possibly fortuitously, this works. This satisfies the relation, and both the total pressure variation and the magnetic pressure variation are of this size. But the length scale variation is satisfied. Okay. So there is no so I said at the beginning, you have to jump through all these hoops. Do you have to jump through hoops to get magnetic buoyancy into the anelastic approximation? As it turns out, no. So whether that is, as they say, possible.
Excuse me, you're
Yes.
no longer sharing the screen on Zoom.
Okay, sorry. Do I have to get out, DM? Is that the?
Thank you very much.
Okay, we're back in business. Sorry about that. Okay. Right. But there is another regime that is in the anelastic, which is that you could have a weak field gradient. So this is the opposite of what I just said. You've got a layer with scale heights of temperature and pressure, let's say, comparable to the layer depth, but you've got a weak gradient of magnetic field. Okay, so HB is much greater than D. Then, if you consider motions on a scale of the geometric mean of D and HB, but with a stronger field than in this one, and that is another perfectly consistent set, asymptotically consistent set of equations. Different. We'll come to. I'll put them up later if you want to see lots of equations, but different. So this is a new regime. So that if one were interested in stabilities of atmospheres with a weaker gradient but stronger pressure gradients, that's what you should use. Okay. Boink. I'm stuck again. Thanks, Kim. Sorry for being useless. Okay. Right, now we can see why Spiegel and Weiss, what Spiegel and Weiss had to do. Actually, Spiegel and Weiss didn't do it this way. Spiegel and Weiss, not surprisingly, did it like Spiegel and Baronis. They argued on physical order of magnitude arguments, which terms should be in, which terms should be out. Caulfield argued like this. And so this is the ordering for standard magnetoboost approximations, that all scale heights are big compared to the layer, and that the variation along the field is long of the order of the scale heights. Now, what you find is that the total pressure variation is tiny, but the individual gas pressure and magnetic pressure variations are not tiny. We'll come back to that when we look at another system. Okay. So this is going back to a point Pat made when he said, you've got the wrong, whatever he said, wrong pressure balance. This is the pressure balance in the magnetoboost ordering. Okay. And there is another, okay, but just like in the anelastic, the standard anelastic, you can have another one which is weak gradient. In the Buoyancy, the standard quote, standard Buoyancy is with a weak gradient. You can do the other regime, which is a strong field gradient Buoyancy, okay, where the field varies across the scale height of the field is the same as the layer depth. Then you have to have, again, you have to have the scale has to be the geometric mean of these lengths. You have a weaker field, but that is another consistent, different asymptotic regime that includes magnetic buoyancy. Then you might say, okay, so where does the Buoyancy magnetoconvection equations fit into this whole game? So the assumption, of course, is that the scale heights of pressure and things are big compared to D. But motions, there's no assumption about the scale of the motions. They are assumed to be on the scale of the layer depth. Okay. And the field, the magnetic field could vary on the layer depth. So the the relation is not satisfied, the length scale relation. And the field is really tiny. So it's interesting, that's never made clear. And you just come along and bung the field in. Those equations are only consistent if the field is really this small, the product of epsilon1 and epsilon2. Okay, compared, say, to epsilon2 here, which is one of the magnetoboost, or even epsilon2 over epsilon1, which is still small, but way bigger than epsilon1, epsilon2. Okay, so the assumption, the implicit assumption in the Boost magnetic convection equations is that the field is absolutely tiny. Okay, then it turns out that total pressure variations and magnetic pressure variations are small. That's why you get delta rho looks like delta T. So that's how they all fit together. Okay. Ooh, there's a table showing how they all fit together. I know I'm going slow. Let me, no, I'm not going that bad. I'm on 19. Okay, bear with me. If you want to see equations, I'm going to show you some. So these are the full compressible MHD equations with no diffusion. 2 parameters, lambda, the ratio of D, layer depth to pressure scale height, and this, which is an alphanic Mach number. Okay, so that's the starting point. So the anelastic equations with magnetic field, which do include magnetic buoyancy, are these. So they're, okay. So this is the scaling that we saw earlier, and the field has to be of this strength. The field has to be order epsilon2. If it's not, then nothing hangs together. Okay. Of course, you could say, well, I could have a huge field. Indeed, you could, but you won't get it into the anelastic approximation. So, the main things are what we've seen before. You've got rho bar here and rho bar here, and the field is more or less as you would expect it to be. Now, if you wanted, so this is the new one, this again is working down a hierarchy of systems. If you're in this weak field gradient, still anelastic, you have to split the field into parallel and perpendicular bits, the perturbation into perpendicular and parallel bits of different sizes. Similarly for the velocity, similarly for the gradient operator. This, of course, as I say, is something that many of you do all the time. So these are the new equations. So if you wish to study anelastic convection with a weak field gradient, these are what you should use. Okay. So they're different to the other guys, but these are an asymptotically consistent set, right? There's no epsilons. This is the first order system of equations. Oh, well, I mean, through those orderings that I had earlier, I mean, it all hangs together.
So in other words, we'll be back to kind of total perturbed pressure balance.
Yeah.
All right, fine. I mean, the cynic's way of looking is saying this with magnetic fields. I mean, of course, you deal with the fast wave, the slow wave, etc. And then you're going, basically, you choose the ordering to eliminate the fast wave, which gives you then the total perturbed pressure balance. So doesn't it come more or less to the same place?
Well, yes and no, because you also have to, it's more complicated than that, because you have to deal with the variation, with the length scale along the field. And if that's not right, you won't get magnetic buoyancy. You'll get a system of equations. Yeah, David.
Isn't there a problem with these equations when at diffusion? In the sense that if I were just to do the hydro case, you couldn't assume that we persistent gradients stay true all the time, because vorticity will amplify indefinitely. So here, if you presume the nonlinearity will also amplify indefinitely without diffusion.
Oh, yeah, I wouldn't advocate solving them.
Well, I'm just saying that that means that there must be some necessary diffusion we can use to limit how big gradients can ever get. And that's another thing that somehow should be incorporated. And if we had some, if we were to estimate how strong the gradients could get, and that would be provided by diffusion, presumably, then you would, then to be consistent, you actually say we need this much diffusion for this approximation to stay true.
Well, my feeling is that, so if we wanted to put the diffusion into these equations, we know we know how big it must be to sit there. And it might be then that diffusion kills off your instabilities and things if it's too small, it's too big.
You want to find the sweet spot where it does grow. You have something within saturates at a level where
Yeah,
it's
but
still consistent. Yes.
that's right. But in terms of the asymptotic ordering, I know what, given what I've got here, I would know how to put the diffusion equation, the diffusion terms in. And I know how big they must be, because to be of interest, they must sit there looking like diffusive terms. And so they must be of exactly the right size to balance the guys on the left. Because if they're too small, they won't be in, and then you'll lead to problems, as you say. If they're too big, they'll just dominate. So there is.
So there's a really.
So I think I'm agreeing with you that absolutely the diffusion will. That's right. The diffusion will have to be linked to epsilon1 and epsilon2.
Magnetic Reynolds number is related to epsilon.
Yeah. Yeah.
There is a symmetry in the system, let's say,
Sorry, symmetry of what sort? I think so. I mean, things that wouldn't be preserved or anything that is where the role of the sound waves are crucial, the fast waves are crucial. So I guess things like that would be preserved. Yeah.
Possibly clarify that question. I think it's a question about variational derivation of the equations so you preserve the symmetries that are inherent in the equations to begin with.
Well, you can. So yeah, well, okay. So you could do this in a variational manner, I guess. So you could start with a Lagrangian or something and try and build in constraints to that. Guess the symmetries would be preserved, but yeah, I guess you'd have to take care of that.
Yeah, if you start with the Lagrangian, you preserve the symmetries and therefore preserve all conservation laws.
Yeah.
And asymptotic expansions, you're often lucky that they do it, but you're not always guaranteed to do it.
It's not easy to do the anelastic approximation, interestingly. So there are some papers by Jeff Fassel, Toby Wood, various people that have tried to do this. And the derivation of the anelastic approximation is not very satisfactory somehow, interestingly. Yeah. Yeah. Okay, I mean, these are just more systems. So that's just another one. Oh, well, actually, that's a Spiegel and Weiss system. Let me just say. So the Spiegel and Weiss system is has one interesting quirk, which comes out nicely asymptotically. It's rather harder to pin it down a la Spiegel and Weiss, this is the induction equation. And the induction equation has a density gradient in it. Normally, of course, the induction equation does not have a density gradient in it. And that, of course, is because although div u is not zero, it says it's zero in Spiegel and Weiss, but it's not really zero. The leading order asymptotic expansion is div parallel is zero.
And in the induction equation, where you've got a div u term from the expanding curl of u cross b, you'll need the next order down. And the next order down involves, so the next order of the mass conservation equation involves the density gradient of the basic state. So this is div u, if you like. Okay, so that's kind of non-obvious equation. All right, so you could say, okay, you've got your anelastic equations. Do they agree with the full compressible equations in the limit? You might say, how could they not agree? Well, they might not agree. They might not agree if there was some sort of something that broke the ordering. If there was singularity, for example, in the asymptotics, you know, something that blew up to promote an order epsilon term to an order 1 term, for example. And why we were looking at this, there is a paper which does actually say that. There's a paper which says that they don't agree, which is interesting. This is a quote from the paper. Even when the expansion parameter is small, it's possible to break the anelastic approximation. So this paper is a numerical study of growth rates of the instability of magnetic buoyancy in the anelastic approximation and magnetic buoyancy in the compressible equations. And what they find is that even, as stated, even when the full compressible system is close to the anelastic limit, they don't get agreement between the two. Okay, so we were interested in that to see how that fitted into what we were doing. So we wondered, could we attack that problem analytically? Now, it's quite hard to, there aren't many cases where you can actually do the anelastic approximation with a field gradient that varies with depth analytically. There is one, beloved of astrophysicists, which is a constant Alfvén speed atmosphere. Okay. So everything varies exponentially and the Alfvén speed is constant. So even though the governing equations, the coefficients are functions of z, they're all kind of exponentials, and you can build that into the perturbations to get yourself a dispersion relation. Okay. So it's a special atmosphere, but it's worth it just because you get an explicit assumption. Expression, sorry. So this is the dispersion relation in that system. Okay, so it's a cubic in omega squared. There are 3 sets of waves. There's a fast magnetoacoustic, a slow magnetoacoustic, and a sort of gravity mode. Okay, and it's the slow magnetoacoustic that is destabilized by magnetic buoyancy. So the question is, okay, that's the full compressible system. Then you can do the anelastic game. You can play the same game with the same atmosphere. And of course, you've lost a pair of modes. You've lost the fast modes. Then you have to compare the two. Do they agree in the limit? Okay, that's the question that we're addressing. So of course, to get from here to anelastic, you have to rescale all these times because omega is a frequency, but it's on a different time scale, remember, in the full system to the anelastic, because the epsilon half to the halves come in. Anyway, of course, it can be done. So you have to rescale the time, you have to rescale the field strength, you have to become close to adiabatic, which this crazy atmosphere means that gamma is close to 1. You have to express the full system in terms of the epsilonic system. And this is what you get. So this is the anelastic. So this is the full compressible dispersion relation expressed in powers of epsilon. So at leading order, you get the anelastic approximation. Good. The anelastic approximation dispersion relation. Good. But that's not really what we're interested in. This is the correction. This is the first order correction. And the question, can you break it? Or is it going to be a consistent limit? Will come by answering, can any terms in here get out of line? Can they become so big that the order epsilon terms contaminate the order 1 terms, in which case that would lead to the limits not agreeing.
So that's fourth order, right? As far as I can see.
Yep.
So what is it? Is it basically the shear alphane and the slow wave?
It's
Got rid of one omega squared.
yeah, you got rid of the fast magnetoacoustic wave.
So then the question is, if you had pure interchanges, you should be able to get rid of another omega squared.
Yeah.
Right? And go because you won't be bending field lines.
Yeah.
You get rid of the alphane wave.
Yeah. But I want to keep it as general as I can. So the question is, can this step out of line? Well, you might think conceivably, because I've got a lambda underneath, or I've got some powers of ma squared here, like ma to the fourth. So you might say, yeah, it could get out of line if lambda was very small or ma squared was very large. But lambda is d over h. That is an order 1 number by assumption in the anelastic approximation. So that does not get out of line. And similarly, the strength of the field is built into the anelastic approximation. So these are order 1 and must remain order 1 for the anelastic approximation. So we believe all is well. We do not agree with Birkhoff et al. For reasons which could be explored, but we do not think, we think all is well. We think that the limit of the compressible MHD equations is captured by the anelastic approximation, which is reassuring to my mind. And these are just, to show that these are just comparisons between the solid and dash, between the two systems, varying as you increase the field strength, you're moving out of the anelastic approximation. So this is where ma squared is 10. It's already quite large, but the correspondence is amazingly good. Of course, once you step out of the anelastic ordering, they don't agree, but I mean, it's one of those, they actually agree quite well even when ma squared is 10. It should be order 1. They're not too bad even when ma squared is 50. So, it all hangs together nicely. Right, conclusions. So there's 5 asymptotically consistent sets of equations, 2 anelastic that both incorporate magnetic buoyancy, and 3 Buoyancy. Interestingly, there is no anelastic, quote, anelastic magnetoconvection system. There is no ordering in which you can, unlike for the Buoyancy system, there is no ordering in which you can exclude magnetic buoyancy whilst retaining, tension terms. Okay, and we believe that in the limit, they agree. The limit is consistent. So going, in terms of interesting problems to do, there's obviously the layering problem. The layering problem I spoke of earlier is what we did, exploited the analogy between double diffusive convection and the equations of magnetic buoyancy in the Spiegel and Weiss limit in the 2D limit. Okay. So it's interesting to see how widespread layering is in the magnetic buoyancy system when you start relaxing those assumptions. An obvious one is to relax it to the anelastic. Okay, sorry for going on a bit. Thank you very much. I'll stop now. You want more?
All right, David.
I'd ask for more.
I was expecting the charge of the light brigade.
Well, I don't know if it's of interest, but are boundary conditions interesting for this problem, or worrying, or difficult, or what? Or are they straightforward?
Well, boundary conditions are always interesting in some sense. I mean, boundary conditions for the layering problem are of interest, actually. as to how you drive.
Once you start going down elastic, then you can't do the trick of Buoyancy where you just say periodic Z.
Oh, absolutely.
You now have
Ab-
boundary conditions.
absolutely.
That's why I asked the question.
Absolutely, yeah. So you'd have to have more, yeah. I mean, depends what problem you're doing. Okay, so when we were looking at like the, you know, the breakup of a magnetic layer, essentially you just set some boundary conditions way up there, because once it hits the boundary, that's not of interest. For these problems where you're interested in long-term behavior, and layering is a classic, as you know well, then it's going to be more sneaky in the anelastic, because of course what we did here was what the double diffusive guys do, which is periodic in the perturbations in this direction. So you have these elevator solutions. Now, whether you can, I suppose you could still do that in the anelastic. I suppose there'd be nothing to stop you doing that. I mean, it's done on the grounds that you don't know what the boundary conditions are. If you have so the layering problem in double diffusion seems to be very dependent on the boundary. So if you have no boundaries, so that you can just have these elevator modes which become unstable, then you just get these nice layers eventually. If you've got a boundary, of course, that messes everything up. And so simulations in finite boxes often don't give you layers.
So you can somehow get rid of the fact that the basic state density not be falling off exponentially. It's still using.
Oh, well, no, maybe. Well, it's only periodic in the. I mean, even in the Buoyancy, the basic state density is linear in Z.
Yeah, I understand that. But
And then you put period.
Yeah, elastic, you can't do that.
No.
And it Buoyancy to understand you do periodicity by this.
Yeah, no, maybe. Yeah, maybe you can't. Maybe that wouldn't work. So maybe, yeah. So then, boundary conditions, I think, would be more. Yeah. They'd probably play a bigger role. You probably couldn't get rid of them to the same extent. Yeah.
Don't suppose the several equations that solve the problem when understood without buoyancy. Does everyone tested this?
No. Well, people have done. Yeah, I mean, people have done magnetic buoyancy in the anelastic approximation. Our concern was originally was whether it's consistent, which it is. Some of these newer systems, no. Yeah, I mean, it'd be nice. Yeah.
Yes. Okay, you mentioned layers can be formed in double diffusive system, and I would like to hear more about it. Those staircase systems, are they sustained in some way, or they diffuse away?
No, they don't. So in the numerics, they merge. So, so I showed one there with like 7 layers or something. You run it forever, then the layers merge until the end you just have one step. But that seems to be a peculiarity of the numerics, whether it is also a peculiarity of boundary conditions. I mean, observationally, oceanographically, these things are observed to be long-lived and robust. Even when kind of waves come through and things, they re-establish themselves. And there seems to be, well, there's sort of a definite scale. So the numerics have not picked out the definite scale at all. It typically starts with lots of layers. There are explanations of different sorts as to why this might even kick in. What you see from the numerics, at least, is that you start with a fairly large number of quite thin layers, and they just merge and merge and merge until you're left with one. But that I'm sure
you know, in the real system, there might be another scale. I mean, that would be interesting, even in the non-magnetic context, to look at that in an anelastic context, where you've got another scale. In the Buoyancy, you're kind of scale free, especially when you've got periodic boundary conditions here. There's nothing externally to impose a scale.
Okay, if you send me some references, that'd be useful.
Absolutely, TS. Yeah. No, there were, there's quite a lot of work on that. Yeah.
Well, you could see if there was you could see if there was a self-sustained dynamo for each of the regimes. I mean, once you're in a regime, you're in it. You can't get out of it. The regime is actually got once you're in it, you're in that regime. So we have to decide. Well, that's the estimate. Not once you're in one of those regimes, it's like when you're a person that's connection. They're linked, you get, you can explain how you get one day.
All right, are you?
Fire away.
So comment on how the Parker instability or what your beloved saturates.
Well, it depends.
In other words, what limits the rise of the magnetic field is really, it's a question of great interest astrophysically.
Yeah. Well, in a way, you don't want it to saturate, right?
No, but that's the point. But I mean, what is, never mind what we want, what is reality?
What is reality?
Of course, you don't want it to saturate because you want to get the loops into the halo, right? But I mean, the question is, in controlled studies, how does it saturate?
Oh, that's reality. Numerical simulations are reality.
Of course.
Oh, I never thought you'd say that. Okay. If you'd said what happens in numerical simulations, that would have been a different question. Well,
Unless
of course.
you have a physical experiment. in the lab.
No. Of course, what happens is that, you know, this is not a very satisfactory answer. Of course, you've got way too much diffusion, and you've got a lid on top of your box, and so the thing rises and spreads out and smears against the top of the box.
So does it always hit the top of the box?
Well, it does in the ones, yeah, but you know, that's not really a satisfactory I mean, it answers your question, but it's not really reality.
And what about a long, have people done tall, thin boxes, for example?
No, I don't think so. No, but you know, no.
All right. So let's thank David again for and when do we resume?